Okay, now we're on question 6. It's quite a long question. So our first question is addition reactions to both alkenes and carbonyl compounds can result in the formation of isomeric compounds. And then part 1, choose an alkene with a molecular formula C4H8, which reacts with HBr to form 2 structural isomers. So structural isomers can be so that can be chain, position, or functional group. Give the structures of these 2 isomers and name the type of structural isomerism shown. So is it chain, is it position, is it functional group? And then outline a mechanism for the formation of the major product. Now, talking about major products, we're only reacting our alkene with HBr. I hope you'll feel happy with instantly ruling out functional group. And then if we're starting with one alkene and making 2 isomers, the alkene isn't going to change, and we're only reacting, with HBr. We're not reacting it with, something with a carbon on it. I think we can rule out chain, can't we? Because there's no way it's going to suddenly become branched if we're just simply reacting an alkene with HBr. So we are looking at a position isomerism. I think that's reasonable to think of from the start, and it's going to help us with this first part. And then outline a mechanism. So let's number the things we have to do. We have to choose an alkene with a molecular formula that reacts with HBr to form 2 structural isomers. We have to give the structures of these 2 isomers. We have to name the type, and we have to outline the mechanism. So, because I'm doing this to try and make things as clear and explain as possible, with C4H8 we have 3 possible alkenes we could choose from. So I want to do this. I want to try and draw this quite quickly, don't I? So we could have it we could have it like this. All right. So the double bond, that would be butanene. We could have the double bond and one more carbon along. And we could have branching we could have something like that. So that would be methyl propene. Methyl propene. So if we think about, we're adding HBr, so it's going to be, we're forming a halogenoalkane, right? So we're reacting an alkene with hydrogen bromide. We're going to be making a bromoalkane. So let's think about, it's going to be the bromine. We've already hopefully worked out its position isomerism. So it's going to be about the position of the bromine. So it's going to be the bromine is going to join one of the carbons that is one of the carbons of the carbon-carbon double bond. So we have to decide, we can think in advance, is that going to lead to a position isomerism or not? The fact that there is a choice of 2 carbons. So let's get a different color. Right, so if it was butanene, it could be that carbon, or it could be that carbon. So would that be position isomerism? Well, yeah, because it would be the first or the second carbon. Right, so they're different positions. If we look at butene, it could be that carbon, or it could be that carbon. Now, we've got to be careful because we would count so that we had that position as the lowest number. So if it was here, it would be the second carbon. And if it was here, it would also still be the second carbon. So that would not lead to two different structures. That would lead to the same structure. So for me, that's already ruled that out, or that has ruled that out. And then if we look at the third possibility, the bromine could form here on the first carbon, or it could form here where the branching is. And that clearly would give two different structures. So we could use this structure, or we could use this structure, right? Both of those would give us position isomers, but the middle one wouldn't. But2E wouldn't. Okay, so I think it's going to be simpler if I go with but1ene. It's just easier, isn't it, to draw a sort of straight chain. So that is my choice, right? My choice of alkene is but1ene. And I'm going to draw it. Sorry, I'm going to draw it like this, because I think it's going to make my life a little bit easier. So you know that the part of the molecule that is involved in the reaction is the double bond. So let's make the double bond as accessible as we can in terms of when we're drawing the mechanism. So that's why I've chosen to sort of keep those all to sort of one side or flat, so that this is all nice and exposed. All right, so this area here is all nice and exposed. And I'm going to be, I'm obviously reacting it with HBr. And what we hopefully remember about that is that is a polar molecule. You don't have to write these delta pluses and delta minuses, but it's to remind us here. And so the first part of the mechanism is that the pi electrons attack the delta positive hydrogen, and then, so remember I said earlier in question 1, which you've hopefully watched that video, is you always draw an arrow from either a bond or a lone pair. So I'm drawing it from the second bond in the double bond, and then my second arrow is from the bond between the hydrogen and the bromine onto the bromine. So what's happening here is one of the carbons in the carbon double bond is now forming a bond with the hydrogen that was in the HBr. So it could be the left carbon, or it could be the right carbon. That's why we're going to get position isomers. Now, they have asked us to give the formation of the major product. Now, so I'm going to draw both possibilities initially, and then I'm going to scrub out one. Okay, so just to show you, so we could have, sorry about that. Oops, we could have this happen. Actually, I could have just written those last two parts as CH2, CH3. I probably should have done that just to save time. It would have been perfectly acceptable. So we would have the carbon on the second carbon in this example would be the positively charged one. All right, so we're going to have a carbocation intermediate. The other possibility, just to show the options, would have been where the hydrogen had bonded to the second carbon. I'm just going to write CH2, CH3 here, okay? Sorry. So what I'm saying is, or what I'm trying to say is, let's pick a different color. This hydrogen has either bonded here or here, okay? Now, if we look at those two choices, one of them is this is a secondary carbocation. I'm just going to write CH2, CH3 here, okay? Sorry. So what I'm saying is, or what I'm trying to say is, this hydrogen has either bonded here or here, okay? Now, if we look at those two choices, one of them is a secondary carbocation. and this is a primary carbocation. And I'm hoping that you remember that secondary carbocations are more stable than primary carbocations. So they are going to be, that is what's going to dictate which is the major product. So our major product is going to be via this structure. So we have our bromine ion still about because the pair of electrons in the hydrogen-bromine bond went onto the bromine. Look, we've got a lone pair. I draw an arrow either from a bond or from a lone pair. I'm drawing it now from that lone pair to the positively charged carbon. And then I get my product, which is H. And I'm just going to do this. Save a little bit of time. I could have done that from the beginning. So there's our mechanism. So that is the major product. Okay. And because I drew what I was doing, and because I drew the other possibility, the other possible intermediate, I can say what the minor product is, or would have been. Well, it is actually, sorry. That's the minor product. And if we were to name these, the major product would be 2-bromobutane and the minor product would be 1-bromobutane. So the 1 and the 2 tells us that they are position isomers. Now, it did help, I think, for me to see at the beginning which form of structural isomerism it was. And I think, you know, this is a sort of question where you might feel that's quite a lot of thinking to have done, and it is a question you can be prepared for. You know, it was a key part of the alkenes topic, was that when you did electrophilic addition, that you could get this form of isomerism. I really stressed it, and it's in my notes for you, and it's in my examples for you. So it is something you can be absolutely prepared for. So have I chosen an alkene? Yes. It is one that's given me structural isomers. Give the two structures. Have I done that? Yes. Have I done the mechanism? Yes. And have I given the type? Oh, sorry, wrong way around. Have I given the type? Yes, of isomerism. And have I given the mechanism? Yes, I have. Okay. So, you know, where you can go wrong here is you just dive in and just draw the first alkene. And if you choose that comes to your mind, and if you choose the wrong alkene, then it's already going to make life difficult for you. So always take your time to get started. And when it says structural isomers, think what type of structural isomerism is there, which therefore are going to be likely, because I think that massively helps you. If you could have determined it was likely to have been position, I mean, it had to be position, but if you thought, I think it's position, because you sort of ruled out chain and functional group, then you've helped yourself massively. Okay, now this is a tricky question, all right? So using HCN and a suitable carbonyl compound with the molecular formula C3H6O. So, you know, you've only got one oxygen. So if it's a carbonyl compound with one oxygen, it has to be a ketone or an aldehyde. Okay, it has to be. If you've got only one oxygen, right? Outline a mechanism for an addition reaction. So if you think about when you did carbonyl compounds, so you did ketones and aldehydes, they underwent nucleophilic addition, all right? So they are giving you information that massively clues you up, all right? So it's an addition reaction, mechanism for an addition reaction, which you've just worked out as a ketone or aldehyde, in which two isomers are produced to give the structures of the two isomers formed and state the type of isomerism shown. So there is a reliance. I mean, this question is going to be easier if you can remember what type of isomerism can form from nucleophilic addition reactions. Okay, and if you remember, we did optical isomerism and then carbonyl compounds, the ketones and aldehydes, and optical isomerism reappeared or featured again in those carbon compound in the nucleophilic addition reactions. All right, so it really helps for you to think straight away that this type of isomerism is going to be optical, and you can do that if you have worked out and got comfortable with the fact it's a ketone or aldehyde and it's addition reaction involving with them, so it must be nucleophilic addition, and you can just make those connections. I mean, this is where, you know, you're studying and feeling comfortable and revising things makes a difference. You can't remember it. You're learning how to apply knowledge, but you need to have that knowledge to be able to apply it. Now, we only have 3 carbons. We've got a carbonyl compound, so we have 2 possible structures, okay? So we could have propanone, or we could have propanal. Okay, so you have a choice, but only one of those is going to be correct. So again, this is a slight reliance on you recognizing that the type of isomerism that could be a consequence of an addition reaction of a ketone or aldehyde is optical isomerism. And that, if you recognize that, and I appreciate that's a bit of an if at the moment because you're needing, you know, you've got to get secure on this, but the fact that you have 2 methyl groups around your carbonyl should be a way of you recognizing, because we have done a question or two that has had that feature, that this propanone cannot form an optical isomers. It cannot form them because for there to be optical isomerism, you've got to have a chiral carbon, you've got to have a carbon attached to 4 different groups. It's going to be the carbon that was in the carbonyl group. Those 2 methyls are not going to change. You are not going to get 4 different groups. So what that means is we have to start with our aldehyde. We are going to be having propanone will not lead to the isomerism that we're looking for. Okay, so we're reacting it with HCN. You've got to appreciate that that is going to be 2 ions in the reaction, okay? So cyanide, you've only used cyanide with when you've done halogenoalkanes and when you've done ketones and aldehydes. With nucleophilic substitution or nucleophilic addition. So what is the feature of the carbonyl the carbonyl compounds that makes them react the way they are? Well, again, you don't have to draw that, but it's to remind us. And remember, an arrow must go from either a lone pair or a bond. So we must draw the lone pair and the charge on the cyanide ion. And then the different thing here is we've got one of the pi bond or the pi electrons moving onto the oxygen. I'm just going to move that structure to that to give me a bit more space. So if we just draw the structure that would be a consequence of what I've just done, that's the carbon that was the carbonyl. It's only got a single bond to the oxygen, but the oxygen now has a negative charge, and we have to draw the electrons that were the pi electrons. Okay, so we're drawing that lone pair there. The cyanide has just joined to the carbon, and then we have our H. So it was hydrogen cyanide we were using. This is where the H comes in. So this is H+. And you will never draw an arrow from an H+. You will always be drawing an arrow to an H+. And that will be from that lone pair on the oxygen. And so then what we get as our product, sorry, I'm going to move it along again, is we are going to get a hydroxynitrile. So when you react cyanide with any of the carbonyl compounds, you get a hydroxynitrile. Okay, so there's our mechanism. Sorry, I didn't do that, the counting. I'll do that in a second. And, you know, like I say, you needed to realize in advance, really, that this was going to be optical isomerism. So have we got 4 different groups around a carbon? Well, we're going to take the carbon that was the carbon in the carbonyl. There's one group. There's another group. There's another group. And there's the 4th group. So yes, okay, we do have a chiral carbon here. So let's go back and number what we had to do. So we had to identify a suitable carbon compound. We had to outline the mechanism. And we have to give the structure of the 2 isomers, and we have to state the... So we've chosen a suitable carbonyl compound, but we needed to do that knowing in advance what the isomerism was going to be, really. And then we have done the mechanism. So now we need to draw them. So I think the way of drawing 2 optical isomers is, I think it helps to draw a dotted line. This is going to be like your mirror. And I think what you should then do is draw a tetrahedral shape. And you've just got to make sure that they are mirror images. And then doesn't matter where the groups go, but like let's go put OH at the top. So we're going to put OH at the top, and we're going to make it look like a mirror. I mean, if I wrote OH again, like O and then H on the right hand side, they would accept that, right? CN and C, CH3, CH2, CH2, CH3, they'll accept it like that. That's absolutely fine. And then H, and then H. So we've drawn our mirror images, but I think, you know, draw the dotted line, draw the 2 tetrahedral shapes as mirror images, and then just add the groups to them, onto them. And then this is optical isomerism. So we have given the structures, and we have stated the type. So we have our 4 different groups attached to a carbon, hence optical isomerism, hence chirality. I just also remind you, we may as well take this opportunity. If you were having to show, if they gave you a structure and they wanted you to identify any chiral carbons, they would ask you to use an asterisk, and so you would asterisk the chiral carbon like that. Okay. All right, now this isn't, I don't really like this question, to be fair, okay? What they want you to say to get 4 marks. But anyway, so they explain why ethanoyl chloride reacts readily with nucleophiles. So I can sort of understand why they've taken the approach they do. So we have to say something about ethanol chloride, but I think we also have to say something about nucleophiles, because it's not just saying why ethanol chloride reacts readily, they're saying why does it react readily with nucleophiles. So we're going to have to say something about both of those things. And then they're asking us to write an equation for one. We have a choice: 1 nucleophilic addition elimination reaction of ethanol chloride. So basically, any reaction with ethanol chloride, because by definition it will be an addition and elimination reaction. And they just want us to write the equation, so they just want us to write the formulae. So let's draw. And sometimes, if you're not sure, you don't know straight from the off what you need to be writing about ethanol chloride, let's just draw it, okay? Now, it said addition elimination reactions and nucleophilic, so anything that's going to be reacting in a nucleophilic addition reaction is going to be attacking that carbon. And why is it going to attack it? Well, because it's delta positive. But it's delta positive. It's delta positive. It actually has it's delta positive because of it being attached to particularly electronegative elements. You need to talk about both of them, right? We are talking about ethanol chloride, so we need to be talking about the oxygen and the chlorine. So that makes, if you think, I know we use delta plus and delta minus, but I think if we've got an electronegative chlorine and an electronegative oxygen attached to that carbon, that partial charge is going to be even bigger, right? I mean, it's still a partial charge, but it's going to be a greater partial charge. So there is a large partial charge. And for you, so you know, when we're talking about partial charges, we're talking about delta plus. So that's a lowercase delta. It means a small change, right? On the carbonyl carbon. So it makes it clear which carbon we're talking about due to bonding, due to being it bonded, due to bonding to, or due to it being bonded to oxygen and chlorine, all right? So that makes it attractive to nucleophiles. But what is a nucleophile? So a nucleophile is an electron pair donor. So nucleophiles have electron pairs that can be donated. It is a little bit clumsy, this answer. I mean, this is what they wanted. I mean, there are different ways we could have phrased this. So we could have said that carbon delta, delta plus carbon can be attacked by the electron pairs of nucleophiles, or the lone pairs of nucleophiles. But you have to make sure it's a pair. And then we need to write an equation. So I think that's 1, I think that's 2, and then we've got 3. So we've got to get the right equation and the right, and it's got to be balanced. So, ethanol chloride, that's what we're going to be, absolutely, we have to react. And let's just keep it simple. Let's just react it with water. So you do have to remember some reactions. And that's going to make our carboxylic acid and HCl, which would be our steamy fumes, by the way. That would be a sign of steamy fumes. Alternative, we could react it with an ester. Sorry, with an alcohol to form an ester. Apologies. Do we always get HCl project? And so, there's a few other things we could have done. So we only need to do one of those. And we get 2 marks for our equation if we've got the correct equation species and it's balanced correctly. So, I mean, that wasn't a very good question, I don't think. I don't really like it, but whether you could get 4 marks, debatable, but I think you should have definitely been able to get 3 marks, okay? I think 3 marks is absolutely doable on that question. But if you have any queries, let me know.